Hello everyone, so today we are going to study about VSBSC, that is Vestigial Sideband Suppressed Carrier. So initially we studied about DSBSC, means your lecturer has taught about you about DSBSC, that is Double Sideband Suppressed Carrier. In Double Sideband Suppressed Carrier, what we are going to do is we are going to suppress the carrier signal so that we are spending less amount of power. In DSBSC signal, we are going to spend power only to transmit the side bands which consist of the message signals, that is M of T. So in the DSBSC, we are going to spend twice the frequency of the message signal to transmit the DSBSC signal. But in order to even reduce this frequency that we are going to transmit, we go for single sideband suppressed carrier. In single sideband suppressed carrier, what happens is, so in DSBSC, one half of the signal, one half of the upper sideband used to occupy the half of the frequency, and other half of the sideband used to occupy other half of the frequency. So in the single sideband suppressed carrier, we are going to either send only the upper sideband or lower sideband. Lower sideband depends upon which sideband you are going to choose to send over the channel. So but what we understood in the single sideband suppressed carrier is, this single sideband suppressed carrier is not an appropriate method to transmit. Why? Because we can see that the USB and LSB are meeting at the same point called carrier frequency, that is FC. But when even though if we send the single sideband suppressed carrier modulated signal over the channel, then at the channel, this is a demodulated circuit. So at the receiver signal, the LPF which is used to get the lower part of the signal, which is having the message component M of T. So after multiplying with the local oscillator AC cos 2 pi FCT with the single sideband suppressed carrier, what we are going to do is we are going to pass sequence to the through the LPF. So in this LPF, what it's going to do is it's going to bring this message component which is at a FC to the, which is going to identify the message component which is at a lower frequencies, and which is going to neglect the message signal or anything which is at a higher frequencies. So the LPF aims to extract the message signal which is at a lower frequencies. So the LPF over here tries to get us the message signal which is at a lower frequencies. And also we can see that both the sidebands meet at the same point, that is at a FC. So at the LPF or for the demodulator, it becomes very difficult to separate this lower sideband or upper sideband. So for that's why we are going to use the VSBSC model, that is vestigial sideband suppressed carrier. So let us understand the generation of SSBSC, that is. So we know that generation of S of DSBSC is nothing but we are going to multiply the message signal with the local oscillator, that is AC cos 2 pi FCT. So when we do that, we get S of DSBSC, which is having two sidebands that is upper sideband and lower sideband, and we are completely suppressing the carrier frequency. And if we pass that through the SSBSC filter, we get S of SSBSC T, that is single sideband suppressed carrier. This SSBSC filter consists of the Hilbert's function. As you all know, this Hilbert functions gives us the complex conjugate of whatever the message signal that we are going to send, that is this. So now this SSBSC, that is single sideband signal, whatever we are getting from this SSBSC filter, we are going to further send it to the sideband shaping filter so that we can get the S of VSBSC T. In the sideband shaping filter, what happens is, so I have taken the example of the USB, that is upper sideband filter. So for this upper sideband filter, the sideband shaping filter further attaches the vestige. These are vestige. These are the vestiges which are attached to the lower upper sideband of the single sideband suppressed carrier, so that so that it overcomes the disadvantage of the single sideband suppressed carrier. In the single sideband suppressed carrier, we had a disadvantage that whenever we are going to send it over, or whenever we are going to transmit it over the channel, at the demodulation we might lose these parts whenever we are going to obtain the message signal from the modulated signal. But in the vestigial sideband signals, we have overcome that problem of losing the information, as we are attaching some of the vestiges, which are called as the dummy sidebands, that are attached to the single sideband suppressed carrier signals, so that we can get the fully working message signal from the modulated signal when you are going to demodulate it. So what is the bandwidth of this bandwidth associated uh, VSBSC? For DSBSC, we know that we used to have twice the bandwidth of the message signal. For single side band suppressed carrier, we used to have only the frequency of the message signal as a bandwidth to transmit it. But in VSBSC, what it's going to do is, we know that in the single sideband we used to have only W, that is as a W or FM as a bandwidth to transmit it. But here we are going to have some W plus, say some this as phi, W plus phi as a bandwidth. So here we can say FM plus phi as a bandwidth which is required to transmit over a transmitter. So this FM lies between FM and 2FM. Suppose if I say as some X, this X lies between FM and 2FM. That's all. Thank you.